Okay. Hi everyone, how is everybody doing? Okay, let's see where we can take this. I know we're coming up against lunch afterwards, but we'll try to do some things and keep you entertained or thinking as well. So, I'm Philipp. I work for Elastic, the company behind Elasticsearch and some other products. You might be using those, but this talk is not really about our products, it's mostly about trade-offs. So we want to talk a bit like, what are the right choices? And the right choices are always a bit more complicated than you might think initially. So what is the perfect data store? What is the general opinion everybody has here? What is often the answer that I get to this one is, it depends. This is normally what you're saying when you're a consultant, because then you start charging a lot of money afterwards. And it depends is a totally valid answer, but what you always need to do is you need to say on what does it depend on. So just saying it depends is not an excuse for not answering something. It's more of the explanation, okay, it is complicated, there are trade-offs, these are the trade-offs we need to consider, and now we try to figure out what is the right answer. But the it depends is an easy excuse to get out of a complicated question. Sometimes people promise you unicorns and stuff. Unfortunately, it doesn't work like that. You always need to pick your trade-offs, because in a complex system, you will have trade-offs. If somebody says like they have this solution, it normally doesn't work like that. Don't trust those. So who knows the CAP theorem? Okay, that's still not everybody. We will get there at some point. So let's quickly do the CAP theorem as one of the most widely known trade-offs, and we'll then get into a different kind of trade-off to discuss. So the CAP theorem is based on the paper by Gilbert and Lynch. Initially, it was a talk by Eric Brewer from Google, and he was basically describing that you have these three attributes, and you want to have all three, but you can have at most two. So the three attributes that you have are consistency, availability, and partition tolerance. And just to quickly think about what they are, consistency in the sense of the CAP theorem is, even though you have a distributed system, it looks as if you had a single instance and you were talking to it and you had a total order of commands. So everything is totally ordered, like you know exactly this command or this operation came first, followed by this other operation. So you have a total order of operations that you are running. That is the consistency part in the CAP theorem. Availability basically means all the instances that you can reach over the network, for example, and that have not crashed, need to answer. An instance cannot decide, I'm not going to answer you because I'm not really sure what is going on with the other instances. An instance has to answer, which you generally want this attribute for high throughput and performance. And then you have partition tolerance, which basically means the network can break and you can lose messages or processes can crash and you're not really sure what is happening. But the loss of arbitrary messages is something you should take into account. And what this basically leaves you with is, since you want all three attributes, but you can have only two at most, that you will have different systems which are kind of falling into different groups. By the way, it's not guaranteed that you will get two of those attributes. If you design a system that is not working that well or has some bugs, you might only get one or zero of these attributes, or kind of a mix under our conditions. So generally, you might have like a relational database, which is more like available and consistent, but it doesn't do partition tolerance that well. So distributing a relational database is normally something that is pretty hard. And it's just depending on where you sit in the CAP theorem of what your trade-offs are, basically. There are two general misconceptions or problems with the CAP theorem that make it a bit harder to understand or a bit more disputable. The first one is partition tolerance in a distributed system is not a choice you can make. Because sometimes people claim like, our network is so good, we don't have partition tolerance, or we don't have partitions, which is not really true. It's normally either you have been extremely lucky or your monitoring is not good enough and you don't see it. Because even the big ones like Google, Amazon, etc., there is a very nice report where they describe basically all the stuff that is constantly going wrong in their data centers. Like how that many nodes died and that many switches fell over and the internet link to the data center was knocked off and the entire data center was offline or whatever. So stuff like this happens all the time. The other thing is that the consistency in the CAP theorem is a different consistency than in ACID. the transactionality, the atomic, consistent, or consistent isolation and durability. That in ACID, consistency is a predicate. It's basically you move from one consistent or correct state to the next. So you have a not null constraint, and you don't violate that. Or you have referential integrity, like you have a reference, and that reference is working and can be correctly resolved. That is the consistency in ACID. It's basically about correctness or having the right predicate. Whereas consistency in the CAP theorem is about time, and that you have this order of operations that you can think. And at one point in time, your entire cluster basically has one view of the entire world. So this is where you're leaning there. And overall, the paper of the CAP theorem paper is very simple. It's not very math heavy or anything. It's very much constructive. So basically it says something like you have 3 nodes and then the network breaks in the middle. So you have 2 nodes on one side and 1 node on the other side. And so you have the network partition, and now your system has to decide, am I consistent or am I available? Because if you keep writing data to these 2 other nodes, this node here has to make a decision. Because if you query it and it knows it cannot see the rest of the nodes, it might be out of date. And then that node needs to decide, am I giving an answer? Then I'm available, but I'm not necessarily consistent because I'm not sure what is happening here. Or if I'm not answering, I am consistent because I'm not handing out the wrong answer, but I'm not available because I basically decided not to answer. And that's the general trade-off that you have here. One thing about the trade-off is also, if you don't explicitly pick what is the right trade-off for you, something random will happen if you run into an error, which is normally worse than having a picked trade-off. Okay. If you want to explain the CAP theorem to your kids or your parents or whatever, you can do it with Robinson Crusoe, because Robinson Crusoe was, I think he was English originally, and he was basically partitioned from the rest of the world on his lone island. So he was sitting there, and let's assume a ship comes by and asks him a current question, like, who is the king or queen of England right now? And then he has to decide, am I consistent or am I available? Because if he is answering, he knows his information is outdated. So if he's answering, he's available, but he's not necessarily consistent with the rest of the world. Whereas if he doesn't answer, he's consistent, but he's not available because he's not answering. So that is how Robinson Crusoe would tackle the CAP theorem. And it's kind of like, the whole problem is very much based on this general idea. By the way, does anybody recognize the island? It's from a movie from the last couple of years. Anybody? Anybody remembers this one? So this was the island where the older Luke ended up on. And we'll stick to Star Wars examples for the rest of this talk. So that's why we have this island here already. You can, by the way, break the CAP theorem, but that doesn't give you a useful system. So if you write to dev null, which will throw away your data immediately, yes, dev null is like, it's always available and it's always consistent in as it's always giving you the same answer. So it's just throwing away your data, which, yeah, it's kind of breaking the CAP theorem, but it totally doesn't give you a useful system. So there is no real or easy way to break the CAP theorem because it's just about this constructive idea of what happens in an error state and how does your system behave. And that's probably one of the most widely known trade-offs you have in data stores or distributed systems. And then we have, internally at Elastic, we have this other theory. We don't have a fancy paper, or at least not yet, and that one is called the fab theory. And the principle is kind of similar. We have 3 attributes that we want to have, and you can only have 2 at most. And then you can pick your trade-offs again. So this is the general idea here. And the guy who created this is Mark, showing him doing his favorite hobby. He came up with the fab theory and gave it its name. So what you have is basically you have the 3 attributes: fast, accurate, and big. Fast is you have something that is answering in real time or near real time. So my assumption is always it's something that a human waits to get the answer back, and you're not going for a coffee or you're not going home overnight to get the answer. That's more like the batch processing system where it takes a long time, or sometimes the Hadoop ecosystem can have that as well, that it might take you a while until you get a result back. We probably want to have a fast answer. So some human queries the data and wants to get an immediate result, like within 1, 2, 3, something like that, seconds, nothing longer. That's the fast attribute that you generally want to have. Then you have accurate. Accurate is you get the exact result back. It's not an approximation, it's not probabilistic or anything. It's, if you do a count, it's giving you the right count. It's not off by 1 or 2, it's exact. It's another attribute that you probably want to have. And finally, big. Big and big data are a complicated term. I will stick to the very simple definition. It's anything that I cannot run on my laptop or a single machine, but something that you need to distribute over more than one instance. So 2 or more instances you need to parallelize. You don't have a single thing that you can query anymore. That is kind of like the big area. But don't do the big data thing. It's very buzzword driven by now, and everybody is doing some kind of big data, and I'm not a very big fan of that term. I will just stick to like saying anything that cannot run on a single instance and needs to be distributed. So otherwise, let's not do any big data hype. Okay, so I assume fast is clear because you wait for it and you get the result back. Big is also kind of clear. It's running on multiple machines, so you don't have a single thing you can query anymore. What is accurate? Like, how can you trade accuracy? Yes, I mean, you can give the wrong result, but is that useful in any system? And I basically want to show you some examples where you can kind of lean more on fast and big and trade some accuracy for that. And my example will be with Elasticsearch, but it applies to many other distributed systems where you can pick one or more forms of this. And the only thing that you need to know about Elasticsearch, if you've never used it, that is the unit of scale, is the so-called shard. So you have an index that is a thing where you put your data, and an index can be broken up into one or more pieces. And one of these pieces can then reside on a different host. So for example, if you break up one index into 5 shards, it could be hosted on 5 different nodes or servers. So you could distribute that. So how to scale is you have the shards, which are broken up pieces of one bigger data chunk. Does anybody know where the term shard comes from? Because sharding is kind of common. Like MySQL calls it shard as well, and a lot of other systems call it if you have one bigger piece of data and you want to break it up into smaller chunks. They call that sharding. Does anybody know where the term shard is coming from? Does anybody remember this one? Most of you look too young. That was, you can see from the resolution, it has been a while ago. It was Ultima Online, and that is at least the story I believe in where shard is coming from. There might be others, but this is one of the older ones I know, and the ones I believe in, is that there was a crystal and it was broken up and it contained like fractions or pieces of the world that you were playing. And all of them together made up the entire world, but you can have one piece and play that piece. And that's where the term shard was legendarily coming from initially. So from the broken up crystal with the shards, this is why everybody calls it shard nowadays. But this is just for trivia. Let's do something more productive. Let's do a terms aggregation. What was the terms aggregation again? It's basically finding the top common terms or most common terms. Like you have the top n terms. Like the top one term would basically be the most common term of something. And I'm using Star Wars again. So this is from the original Star Wars movie, or the first one, or I don't know, the naming got complicated. I think it's version or number 4 nowadays, but it was the very first one that was made. And somebody counted how many times do specific Star Wars terms appear in that movie. So you can see Luke was the most common one and appeared 64 times, and R2 appeared 31 times, and Alderaan 20 times, etc. So this is the distribution of how many times the terms were appearing. And what I'm basically doing is I have 64 documents with Luke and 31 with R2, etc. And I basically want to count which one is the most common one. So pretty simple. So I create my Star Wars index. It has 5 shards, so it could be spread out over 5 nodes. And then I put in some documents. You can see I have the first row here. It's basically the meta information. So into the Star Wars index, I put a key or the document, and this is the actual document. So we have 64 Lukes, like 64 times Luke, and then we have 31 R2s, etc. So we have a lot of those documents. And then you could see like what is one of the common ways to see how what is the most common term is you could, for example, do a tax visualization. So let's quickly do that. We have a tag cloud here. I just say I use that Star Wars data. Let me make this slightly larger. So right now we have everything together, but I want to break up on a specific tag, and that is a terms aggregation. We'll see the actual query in a moment, and I want to use that on that word, which was basically Luke or whatever, and I want to have the top 20 most common terms. And then it will give you something like this. So this is a pretty common aggregation where you actually basically just see like what are the most common terms, and then you have this tag cloud visualization, like the larger an item, the more common it appears. This one is, by the way, depending on how you implement it in Elasticsearch, it might be exact or it might just be an approximation. And for many use cases, even if it's slightly off, the approximation is fine. But let's see what is actually happening here on the query level. So what we have here is, so let me quickly, I'm just searching for all the Lukes. And if I search for that, you can see I have 64 Lukes in my data set. So this is the number of documents I've inserted, and this is working well. But now I want to run this aggregation. So you can see I'm running an aggregation. I call it the most common aggregation because I'm just interested in the most common term. I have one field that is that word field, basically, that I want to aggregate on. And size 1, this one here basically says, like, I want to have the top one term, like the most common one. And this size down here basically means I don't want any of the actual documents coming back. I just want the aggregation result, because the individual documents I don't care for much. And if you run that, how many loops should there be? 64. If I run this, what you're getting is 60 loops, which is weird. Like, why are we counting wrong? And you also might be saying, so for some reason we are counting wrong, and it appears like this is a very simple example. Why are we counting wrong, or what could be going wrong here? So normally this wouldn't happen. I have cheated slightly to kind of show you the problem that is happening here. So what I've done here is when I inserted the loops, I made sure that we have this routing information here. And this routing information is basically telling it to which shard the data goes. Normally, if your data is evenly spread across all your shards, you wouldn't run into this problem. But I have kind of skewed my data and made sure that the first 10 documents, so 0 to 9, they are evenly distributed with a different routing key, but all the 54 other documents are going to the same shard. So one shard has almost all the Luke documents, and the other ones have very few. And we will see in a moment why this is actually giving us a wrong calculation then. Because how we make sure where the data is going, basically we take the routing key, we hash it, we calculate it modulo the number of primary shards, and this is the shard where this goes. So our data is not evenly distributed because we hash 0 million times, calculated modulo 5, and then it always goes to the same shard. By the way, why am I using a hashing algorithm here or function and don't use the routing key directly? So generally, if you pick your own keys, for example, if you use some string, E would be the most common letter in English, and then you might have a lot of things or documents starting with E, or the ID starting with E, and then you might have a hotspot in your data. The idea of the hashing function is that your data is evenly distributed amongst your entire key space, and then you can break it up into even chunks. I've just kind of like broken that a bit by using the same routing key all the time, which you shouldn't do, because if you skew your data like that, a lot of data will go to a single shard, and it will not be evenly distributed amongst all your shards. And then you can also look at that information, and you can see, for example, this shard here has only 26 documents, and this one here has 70 documents. So you can see the data is not really evenly distributed amongst them. And that is kind of what is happening here. Because how do we actually do that aggregation? So we have 5 shards, and every shard is calculating its own sub-result. But if I have this terms aggregation, and let's assume I have 1 million terms in each shard, it would be very expensive if I wanted the top one result, and I actually do the aggregation for all 1 million terms that I have. So rather than calculating all 1 million terms on each single shard, we don't calculate all of them. What we do is actually, we only calculate the top shard size. And the shard size calculates the size. This is the number of documents or the number of top hits you want. So in our example, it was 1. I want the top 1 hit. I multiply it by 1.5, add 10. And that is how many results each single shard is giving me back. To what does this come out in our example? So we have 1 times 1.5 plus 10. And then we need to round, because we need to give an actual, like we cannot use a floating value for the number of results. Will it be 11? Will it be 12? It's rounded down. So you will get 11. So basically, every single shard gives you back its top 11 results, and then we coordinate those together. So you get from all the 5 shards, you got the top 11 results, and then you calculate those together. So 11 per shard. How many sub-results are we aggregating in total? 5 shards, 11 results each, so basically 55. If you had lots and lots of terms, this would be much more data to calculate on each single shard and then aggregate. So this is definitely an optimization that is making your data faster and also doesn't blow up your memory or heap here. But this is why we are getting to that wrong result. Do you already see where the problem is coming from now? Since I have almost all the looks in one shard, the other 4 shards have very few looks. And I've created the data in a way that other documents are more common there. So if I only take the top 11 results, there might be some looks on the other shards, basically, that are not in the top 11. That's why we don't transfer them. And then basically you aggregate. You don't have look in the top 11. You get 0 results, basically, from that shard, even though there might be 1 or 2 looks in there. And that's exactly what is happening here. You can, by the way, show the error bounds a bit better if you add show term. So let me slide this a bit over to make it more readable. It's the same aggregation, but here I say show term doc count error. And when I run that, it tells me, well, you have at least 60 looks, but I know there might be 4 more. How do I know that there might be 4 more? Because basically I know every single shard is giving me its own top 11 results, and then you know the 11th result has, like, let's say 2 hits. And then you know the 12th result could have also 1 or 2 hits. So this is basically the error bound that this shard is adding. And then you just add from all the shards that don't give you a look back, you calculate what was the top result that you got back, and that is basically a maximum error bound you could have. Also, if you calculate that for all the shards, this is the maximum you could be off in total. And these are all the documents that are not included in your aggregation. So these are all the non-look documents, basically. So we have 228 non-look documents. We have at least 60 looks, but it could be also 64 looks. This is basically what we're saying here. And then you can trade some performance or overhead for more accurate results. So what I'm doing here is I set that shard size to an explicit value rather than relying on the default calculation and ending up at 11. I'm saying, give me 20. Since I only have 20 documents, this must be exact. If you run that, it will actually say, like, okay, I found 64 looks. There were 0 errors left. So this is the right result. But the calculation was a bit more expensive than it would have to be. So this is kind of the trade-off that we're picking here. Like, we're calculating more results, but the result will be more accurate. And you can basically tune that yourself, like, how much performance do you want to sacrifice for more accurate results? And does it matter for your use case? Because, for example, in my visualization here, you probably couldn't tell if this one has 60 or 64 documents behind it in terms of size. Like, the approximation is probably good enough the way it is. OK, so this was the terms aggregation. Let's do a cardinality aggregation. What was cardinality aggregation again? That was the number of unique terms. So in our sample, we only have 16 unique terms. So we have look and R2 and 14 others. So we have 16 unique terms in total, and we want to calculate this. What would be the naive approach to calculate this? Yeah, you could just do a count. So what you probably would do is you have a hash set. So you insert something into a hash set. If it has the same value, it will end up at the same key and overwrite the other one. So you basically have a list with no duplicates, but you have all the unique terms, and at the end you can just do a size on that. How will that perform? Not very well, because it will just scale linearly with the number of terms you're counting, or the number of documents you're counting. So what you end up doing then is both the computations will grow linearly, like n, but also the memory use for the unique terms will increase linearly n. What you probably don't want to have, like if you have 1 million unique terms, this might be very expensive and you don't want to pay that price. So how could you do that in a more performant or clever way? So something you could do is you could then have something like an estimator. What I'm doing here is we're using a hash function again, and we are hashing to a floating value with 2 numbers precision behind the dot. And basically, we're calculating here, we are hashing a value. We remember the lowest value, and we only remember the lowest value. So we don't remember all the values, but we just keep track of a single value. Basically, we hash Luke, we remember for 0.44. We hash R2, we figure out it's higher, so we forget that value. We hash Jedi, you see this one is lower, so now this is the value we remember. Luke is higher again, so we throw away this one. And what you do then to calculate the cardinality basically is, because of the even distribution of your data, ideally, you take 1 divided by the minimum value, and that will give you approximately how many unique values you will have if the hashing function is fair. So 1 divided by 0.007 equals 14, like we have 16 unique terms in total, but this is kind of good enough. This is just a made-up example. This is not, I don't have a specific hashing function behind this, but this is the general idea of how a simple estimator would work. You hash everything, you remember the lowest value, you calculate 1 divided by the lowest value. This is approximately how many unique terms you have. But the error bound is still pretty high, so you could do something smarter. You could do probabilistic counting. Probabilistic counting is basically you hash, have a binary representation, and then you count the leading zeros. And leading zeros are basically counted from the right-hand side in this example. So here, for example, let's assume I have 3 bits, and all the possibilities. How many possibilities do I have with 3 bits? 8. Basically, if something has 3 leading zeros in its data set, then there is a high chance that it has 8 unique values. So 1 divided by 2 to the power of how many leading zeros you have. You count all the values in your data set with the leading zeros. The highest number of leading zeros is that k here, basically. And this is approximately how many unique values you have. And this is a probabilistic counting approach. But it has quite a bit of variance, because if you randomly have one with 1 0 less or more, you will have quite a big jumps. Like, this is not very fine-grained. Like, this will be a bit jumpy in how many unique values you have. What you could do instead is, and this is the approach that is known as log-log, you don't just have one hashing function, but you use multiple hashing functions. And then you basically even them out. So here you can see the green area, that would be you have one hashing function, and you can see, depending on where you fall, basically you could be further off the actual cardinality. If you have multiple hashing functions, it's like the gray area, so it will be the band will be less wide, and you will have a higher chance of kind of hitting close to the actual cardinality. Will it be expensive to run every value through multiple hash functions? Yes. Do you want to do that? No. So we need to find a smarter way. And what log-log is basically describing then is that you bucket. Basically, you take the binary representation of the hash value and you use some part of it to bucket. So you make multiple groups. And then basically you even out over all the groups. And the rest of the value you can use for counting leading zeros. So here you can see these 4 bits we use for grouping. So this is group 4, this is group 9, this is group 0. And then you count how many leading zeros do you have in each group. And then you count like what is the highest number of leading zeros in each bucket. And then you average out over all the buckets how many leading zeros do you have and how many unique values do you have because of that. So you can see here, bucket 4 has 3 leading zeros, bucket 9 has 4 leading zeros, bucket 0 has 1 leading zero. And then you average those out, and you get reasonably good results. This is the actual pseudocode to calculate this one, but we can probably skip over that today. And then Google came along and said, like, LogLog is interesting and works okay, but the error rate is still too high. And we have found an optimization to actually get the error bound below 1% for most use cases. And that's what they called HyperLogLog. And then there was another small improvement, and now it's called HyperLogLog++. And this is the one we use. And it's quite a mouthful of a name, but this is what you get. But it's very fast, and it's pretty accurate. That is kind of the thing that we have here. So let's try that out to calculate here. So in my code was this visualization looks like, here I call this the type count. It's a cardinality aggregation on the same field again. And here I can tune the precision again. Basically, tuning the precision means up until this value, this will be an exact value. For higher cardinalities, it will be an approximation, and it might be slightly off. Since we have 16 unique values, if we run this, it will give you the count that is off by 1. So it says it's 17. So it's kind of close, but it's not exactly there yet. You can tune this. The default value for the precision is 3,000. So if you have 3,000 unique values, it will be exact. Over that, it will be an approximation. And we have kind of like a maximum for that. You can set it to 40,000. If you set a higher value, we will still cap it to 40,000, because otherwise the computation gets too expensive. So we don't want to have that. And you can very easily calculate how much memory you need for this calculation then. Basically, you take the precision threshold times 8 bytes, and that is how much memory you need for this calculation. So you can very easily infer like how expensive one specific calculation is for you. This is when we have tested it with multiple thresholds and what the error rate is. You can see if I have a precision threshold of 800, so I'm just using 800 bytes, then the error rate can go up to like 6% or so. If you have 10,000, so you have 80 kilobytes for the calculation in terms of memory use, then your error rate is 1% or maybe slightly more than 1% in times, and close to 0 for the rest. So this is how the optimization works for that. Now, if I tweak that in my example here, you can see already if I set it to 12, then we're getting 16 values out of this one here. So you can tweak it slightly to get the right result. But we don't have to do a hash map where we calculate all the values, but we can just extract like an approximation that is probably good enough for the number of unique values. Where this might be useful is, for example, if you are working for a security use case and you want to know how many unique IP addresses have connected to a device, or how many unique domain names have you been reaching out to. Their cardinality calculations can show you some stuff. Just as one example for them. Should you pre-compute the hashes? Like you could pre-compute the hash and then just calculate the zeros rather than always hashing something. What is the right answer for that one? It depends, yes. I think we need to work on that a bit more. That you always say, first it depends, and then you need to say on what does it depend on. So what does it depend on in our case here is, if you have a very large data set and it has a high cardinality, then pre-computing the hashes might pay off. If you have a small data set with lower cardinality, or if you have a low cardinality or a numeric field, then it doesn't, because hashing numeric values is generally very quick in modern CPUs. Then it generally doesn't pay off to pre-compute anything. So you need to figure out what is the right data set, and then you know I should pre-compute or not. There was another improvement in there that was called LogLog beta. We had a pull request, we tried it out. It didn't improve the results. We never merged the pull request because it didn't go anywhere. There's another improvement that we haven't tried out yet, which is called HyperLogLog sketches. There's a paper. We haven't tried out the code. We're not sure yet if this might be an improvement or not in the long run. Maybe we get to implementing that, but HyperLogLog++ is working okay for most use cases anyway already. But yeah, if you're into papers, this is something you can look into. Okay. Now another problem around search, because Elasticsearch is widely used for search, and sometimes relevancy looks as if it's broken. So relevancy is basically like, I search for something, I get some results back. What is the most relevant result for my search term? So let's say we search for Luke, and you will see something weird here. Like, I search for Luke, all the documents that I have in my dataset just contain the word Luke. So they should all be the same in terms of relevancy, right? But when you run this, you can see this one here, this Luke, So this is my document, Luke, has a relevancy of 3.2. And as I scroll further down, you can see this Luke here only has a relevancy of 0.7, which is weird because it's exactly the same document. How can this one be less relevant than the others? Where do you guess stuff breaks? Because of the shards, of course. So how do the shards play a role here? So let's see what is broken here and how we can fix that one. So how the general how we calculate the relevancy of documents is called TF-IDF, term frequency, inverse document frequency. It has three main components. The first, or the current implementation is called BM25 for best match, but it's very similar. It has just tweaked some things. The first thing you do is, if I search for Luke, and one document contains Luke 3 times, it's more relevant than a document that contains Luke once. Is this relevant for my use case here? No, because all the documents only contain Luke once. But in theory, it would look something like this. If you have Luke once, the relevancy is something like 1.1. If you have 5 Lukes, the relevancy will be higher. The change in the newer algorithm is that we assume that once you have reached approximately 5 or 7 Lukes, it doesn't improve much anymore. Whereas the classic approach was 20 Lukes are much more relevant in one document than 5 Lukes, which is debatable. Then we have the inverse document frequency, which is basically saying terms that are very common are less relevant than terms that are rare. Like rare stuff is always valuable. So what you get here is basically over all the documents that you have, how many times does Luke appear? If Luke appears only a couple of times over all the documents, it's much more relevant than if Luke appears hundreds of times or 1,000 times. And this is also where it breaks, because these statistics are by default done on a per shard level. That's why this breaks. And then we also have something called field length norm, which basically means if your search term appears in a short field, it's more relevant than if it's in a long field, which is kind of intuitive. So if you have a title and it has 5 terms and you have the body which has 1,000 terms, if your search term appears in the one with 5 terms, it's probably more relevant than the one with 1,000. But this doesn't matter here because all our documents have a single term, so it doesn't make any difference. And how we actually fetch the data is that to query in Elasticsearch is a 2-step approach. What you get is you have a so-called coordinating node. In this example, this will always change. The coordinating node is this one here. So the query comes into the coordinating node. It figures out I need to query, we only have 2 shards here. I need to query 2 shards, shard 0 and shard 1. It will ask the shard like, hey, I'm looking for the top 10 Lukes. Give me your top 10 Lukes. And then the coordinating node will get a list of the IDs and the scores of the top 10 Lukes of each shard. And in a second step, the node will then reach out to the shards again and say, hey, overall, these are the top 10 Lukes. Now give me the actual documents for these documents. This is the top list in general. And it will get that back. If you have 20 shards, of course, you will need to get the top 10 results from 20 shards. That's why we don't fetch all the document immediately, but just get the IDs and the score to figure out what are the right documents, and then just in a second step, fetch those right documents. The problem here is the statistics of the inverse document frequency. There is no step to actually make sure the statistics are the same and evenly distributed over all your nodes. So you don't have those. You could add a parameter called DFS, query then fetch. So basically, you have 3 steps. First, you go to the nodes and tell them, hey, let's figure out what are the statistics, how many Lukes do we have overall. In a second step with that information, you then query like what are the most common Lukes, and then you fetch the actual most common Lukes. And to show you just how this looks in the query, so here we add this long parameter, search type, DFS, query then fetch. If I run this, you can see now the first Luke has a relevancy of 1.5, and the 10th Luke still has the same relevancy. Should you use this parameter for your queries? Should you use this parameter for your queries? It depends, maybe. Actually, for this one, I'm not sure. For this one, our documentation is pretty clear. So first off, yes, we solved this one. Then people always ask, like, how much performance will this cost me? This is my favorite comic for any performance benchmarks. especially when you benchmark something against a different vendor, because that is what every vendor is doing with their competition. They find similar conditions where their product is doing very well and the competition isn't. So be careful with any benchmarks like this. Yeah, don't do this. And it's very hard to tell you, like, DFS will cost you X% in performance because, yes, you have one other network round trip, and your terms will need to be in memory, and how long does it take to calculate that? So it's not easy to say, like, it will be X%. But it will depend very much on your environment. But our documentation is not very much on the it depends side. It just, DFS shouldn't be used in production because it's not required. Because normally, if you have a regular data set, your documents will be evenly distributed over all the shards, and that's why you don't have to do this. So most use cases don't. Even though you know how you would fix it if you have a special use case or skew data in some way to actually make this work. And then, what happens if you use a single shard? This is, by the way, the new default that we have in the latest version. So our tech lead of Elasticsearch, Simon, always says use a single shard until it blows up. And then you figure out how many more shards you will need. And what are you trading here now? If I go down to a single shard in the fab theory, the big, because we cannot parallelize anymore. But we will get more accuracy for that. So this is how you can easily tune that as well. So let's quickly, since we only have 5 minutes left, let's do that. So basically, I'm saying my Star Wars index is read-only, and I take the data and put it into a new index. So the new index is called starlet wars, because little star, and it only has a single shard. And then I basically shrunk this down. So the Star Wars index was shrunk down to starlet wars with a single shard. And then I can start searching. For searching the full-text search term Luke without the DFS query then fetch, will this give me the right result now? Yes, because IDF, it's a single shard, so the statistics are right. So if I run this, you can see here, all the Lukes have 1.5 something, they're all the same. If I run the terms aggregation for the most common term, will this be correct? Yes, because I get the top 11 results. Since I only have a single shard, the top 1 result will be in the top 11. So this one is correct as well. So here you get 64. This one here. If I run the same for the cardinality aggregation, will this one be exact, yes or no? No. Because this one is still probabilistic. We still don't do the hash map and count all of them. This one is regardless if you have a single shard or multiple shards, this is still a probabilistic one. So you will kind of need to know how the algorithm works to figure out if something is exact or not. And you can see this one is still off. So some people might also say this was kind of a cheap trick, because with a single shard you don't have the big part anymore, so we traded that away. So to wrap up, it's all about the trade-offs. There is no single best system, there is no single best approach. It will really depend on what you need to do and what your trade-offs are. And you will need to figure out what makes sense for your use cases. So you have the cap theorem, which if something breaks, how does your system behave? The fab theory is more like, how do you trade accuracy for speed and scalability? And then you need to pick what is the right one. How much accuracy do I need? Or how quickly do I want my results? Or how much scale do I want to have around them? And these are the kind of like trade-offs you need to pick, not only in Elasticsearch, but in many other systems as well. You just need to make them explicit and figure out what are the trade-offs that you're faced with. And with that, I think we have 2 minutes left for questions. If you want stickers, I have quite a few stickers here. I think I'll also go to the discussion zone afterwards, so if you want to skip the initial lunch queue, come to the discussion zone afterwards. Do we have any questions on Slido? Okay. So. Yeah, okay. How many shards should we use? What is the answer to that one? It depends, obviously. And this one is very tricky. So shards are generally how you can scale things, but shards also have cost to them. So having too many shards will be costly. And oversharding, having too many shards, is one of the most common things that people do in Elasticsearch wrong. That's also why we changed the default to 1 shard. generally, as a rule of thumb, your shards should have somewhere between 10 and 50 gigabytes of data, one shard. It could even go up to 100, that also works. If you have like 500 gigabytes in one shard, it might get tricky also. If you need to move that shard around, it takes a long time. But make sure your shards are in the gigabyte range. If you have shards that only have kilobytes, you're wasting memory and file handles, and we cannot compress stuff in the background well enough because it's too little data. So gigabytes for shards in general, as a quick rule of thumb. Which version of Elasticsearch has HyperLogLog? We would need to look at the pull request, but pretty much forever. I would say 4+ years. Or to phrase it another way, any version that you should be using has it. If you're using a version that doesn't have it, please upgrade, because you're really running on something that is dead. Should we use SearchGuard or not? Sorry. What does DFS query and fetch do in the extra trip? So basically what you do is you go to all the nodes, you ask them like, how many looks do you have? You get back to that coordinating node. The coordinating node says like, over everybody, we have 64 looks. And then it can calculate for the IDF part, well, how many looks do you have and what is the right calculation for that one? So that is pretty simple. Should we use SearchGuard or not? I don't do troll questions. Yeah, you will know the answer to that one. Otherwise, come to me afterwards and we can discuss in private. But no, this one not. Why not call SaaS speed, availability, scalability? Interesting. I don't know. Mark came up with Fab. That's why we stuck with that. But yeah. We can
Future ideas.
Yeah, we will think. I mean, we don't have a paper yet, so we might come. If we write the paper, I will let you know what we come up with. Using a single cloud can only give up on speed in favor of size. I mean, the total size will not so much depend on the number of shards. The only thing that you might be losing out if you have very, very little data in a shard is that we cannot compress data. So that some data structures are compressed in the background. So if you have one term that appears many times, we can compress it a bit. So that will make your data also more compact. But generally, the shards are more for scalability. Like you can distribute data over multiple nodes for writing especially. For reading, you generally want to have replicas because you can read from any replica. I hope this answers the question. If you want to do more sizing and number of shards, just find me afterwards and we can do that. Enjoy lunch.
Thank you very much, Philipp. This is for you.
Thank you.